0 is u naught of x. I'm not writing the rest of the details actually, that omega is a subset of Rn, where n is less than or equal to 3, and the gamma is the boundary of the domain actually. Let's do one thing. Let's multiply this equation. I want to show that the solution of this equation, so the claim is, okay, so let me write the claim in a minute. The claim is that basically that the solution to this equation is a gradient flow actually. But how to prove that the solution to this equation, this evolution equation, is a gradient flow? You need a gradient system actually. So you need to identify a gradient system and prove that it is indeed a gradient system. Okay? So in order to do that, what you need to do, you have to, by the way, what we know about this problem, for this problem we have discussed many things. We kind of proved that this solution, this equation has a global solution. For any u naught you take from H, that H is say H2 intersection H1 naught. So if you take any u naught from this initial condition from this space, then there exists a unique global solution, okay, to above evolution equation, u that is continuous in H, okay, where H is this, and differentiable in L2. Okay, so its weak derivative exists. So we have this. But in fact, if you take your initial data a bit more regular, then you can have even more regularity of the solution actually. Okay, but for us this is enough for now. So let's do what? Let's multiply this equation, say, with u of t, and then integrate with respect to x. In other words, take the inner product of this equation with the time derivative of the u. So if I take the inner product of this with u, where this inner product is in H is in L2, it's an L2 inner product. Okay, ut is equal to Laplace u ut plus ut and minus u cube ut. Okay, so we have discussed it several times that this will become what do we call ut square. Okay, this I can pull the time derivative out. Okay, the penalty is that I need to put a 1/2, and then on Laplace u I can apply the what do you call integration by parts. So I can have d by dt. The first term will become d by dt over the integral of the gradient of u square dx. So this is what the first term will become actually. Okay. How to do it in detail we have discussed it several times. How about this? So I can pull the time derivative out as well from here, and then it's going to be the integral of L2 norm of u actually. So it's going to be omega u square dx, and the last term, okay, so you need to put a penalty 1/2, and the last term will become what do you call 1/4 of d by dt of what? Of the integral, okay, of u power 4 dx. Okay, so this is what is going to be final. So if I put it in a more concrete term, if I multiply both sides, for example, I minus by minus and put all these together in a single term, then I can say that this is same as d by dt. By the way, this would also be negative actually. Okay, because after applying the integration by part, this will become negative gradient u gradient u. So if I multiply both sides by minus and put these integrals together, so you're going to get the integral of 1 over 2 the gradient of u square plus 1/4 of u power 4 minus 1/2 u square dx is equal to what you call minus ut square. This is what is really the equation is going to take form. Now this guy, we identify this, or we can identify this as the energy, okay, of the system driven by this evolution equation. So this is the energy of system. Okay, energy of the system. Let's give this integral a name. So let's call it E of u. Okay, E of u is the integral for omega of 1/2 gradient of u square plus u power 4 by 4 minus u square by 2 dx. Okay, this is what is going to be. And now it's time to put a claim. Now it's time to put a claim. What is the claim? Let's call this problem the problem star. Okay. The claim is that u of t, where t bigger than or equal to 0, the unique global solution u of t, where t is bigger than or equal to 0, star is a gradient flow. So this is what my claim is. That's a gradient flow. That is, and how can I show it? That the triplet H2 intersection H1 naught, in other words the H, and the semigroup corresponding to the global solution, and E, the energy of the system, is constitutes a gradient system. So that's a gradient system. Okay, that's a gradient system. In order to show this as a gradient system, we need to show first few things. Number one, the first thing should be to think that why E is Lyapunov. Okay? Why E is Lyapunov? The answer is pretty much simple. The first step would be to show that E is Lyapunov. Actually, the answer is pretty much simple. So E is this integral, okay, integral of polynomial. E is a continuous map. Actually, so there is nothing in this expression that can create a trouble. Actually, so this is a continuous function of time. Actually, so if you treat each of these as E as a function of time, it's continuous actually. Now E of u is a continuous function. What is the next thing? The next thing is that your E should be non-increasing actually. I mean, if you see this equation, you can rewrite this equation as d by E of u of t dt is equal to negative of ut square actually, equal to minus ut square. And this guy is for sure less than or equal to 0. So this means that E of t is decreasing over the time actually. Okay, it's decreasing, it's non-increasing over the time. So E of u of t is non-increasing over the time. So this is what you call the first condition of E being a Lyapunov function. The second condition was to show that E as a function of u, okay, as a function of u, as a function of x, has a lower bound actually. So this is an exercise for you to prove for yourself. The exercise for you is to show that E of u is a lower bound. Has a lower bound actually. Has a lower bound. Okay, has a lower bound. Hint for doing this is to use this what do you call version of Young's inequality. So you can use this inequality. So u square is less than or equal to u power 4 by 4 plus 1 actually. Okay. So use this Young's inequality and try to find a lower bound for E of u. And it's not a difficult thing to do. So what does this is going to show? This is going to show that your E is Lyapunov. E is Lyapunov. So what remains to prove that that E that this triplet is a gradient system. So what remains to prove is the two conditions of the definition of the gradient system actually. Okay? Definition of the gradient system. So let's think about the condition 2. Okay? The condition 1 is a reading exercise from notes actually. So, you know, read it proof for yourself. What was the second condition in the definition of what do you call the gradient system? Is that if you have V of, so if you have an instant t positive such that V of s of t operated onto some x is equal to V of x, then x is a fixed point of s of t. So it's a fixed point of something. Okay, so this is the second condition that we would like to show it. Okay. So here's a proof of 2. Proof of 2. So what is the proof of 2? The proof of 2 is that consider, suppose there is a T naught, okay, T naught, such that E of S of T, say U naught, okay, is equal to E of U naught. Okay, E of S of T of U naught is equal to S of T of U naught. So we assumed this, and I would like to show that now U naught is a fixed point of S of T. How can I show it? It's not a difficult thing to show. I will say again that consider this identity. Okay, so let's give it some name. Let's call this equation eta. Okay, so in order to prove this, so you have this assumption, and you want to show that u0 is a fixed point of what you call semigroup. So I'm saying that integrate the eta from 0 to t. So integrate the eta from 0 to t. Okay, or maybe 0 to t naught actually. Okay, 0 to integrate from 0 to t. So integrate this from 0 to t. So we're going to integrate this from 0 to t. So you're going to get e of u of t minus e of u naught is equal to integral minus integral of 0 to t norm of ut square beta. Okay, this is what that you're going to do in general for any t. Now, in this instant, if you, for example, substitute e of t naught actually here, e of t naught, then I know that these two guys are equal. These two guys are equal. Yes. Alright? These two guys are equal. So if these two guys are equal, that means that their difference is equal to 0. Okay? And what does this imply? That this integral is 0. And integral is non-negative. So the integrand would be 0 actually. So u of t is 0. Or this square is 0. And if the integrand is 0, what does this mean? That ut is 0. Its time derivative is 0. Okay? And if time derivative is 0, so what does this mean? That means that u of t must be constant actually. So if you integrate this with respect to time, we're going to get that your u of t is constant. Okay? So if it is constant, what does this show? By the way, I know this constant, so this is constant for all t bigger than or equal to 0. I know this constant at u of 0, and this is u naught. Okay, u of 0 at t equal to 0, u of 0 is u naught. So you're going to say that your u of t is equal to u naught for all t bigger than or equal to 0. But you can also write your u of t as s of t u naught. Okay, by definition. So if your u of t is s of t u naught and it's equal to u naught for all t bigger than or equal to 0, tell me what is your u naught. U naught is a fixed point of semigroup. Okay? It's a fixed point of semigroup. And if it is a fixed point of semigroup, you have the second condition of the gradient system is satisfied. So this means that this guy constitutes a gradient system. And if it constitutes a gradient system, the u has what do you call? U has what do you call? U is a gradient flow actually. Okay. By the way, I would like to add one thing. One last remark into both, that if u of t is u naught, then and u of t is 0, and u of t satisfies what do you call your evolution equation, okay, then u naught would also satisfy that evolution equation. So it's going to be stationary version of it, delta u naught plus u naught minus u naught cube and equal to ut or u naught t that is equal to 0. So what does this show? That the fixed point of the semigroups are basically the stationary solutions of the evolution equation. Okay, stationary solution of the evolution equation. And finally, since this constitutes a gradient system and u of t is a gradient flow, so we know that in long run, the solution of your nonlinear evolution equation will converge to the elements in omega limit set. And the elements of the omega limit sets are the fixed points of the semigroups. And the fixed points of the semigroups are the solutions to the, what do you call a stationary equation. So in other words, if you want to find, what do you call, the solutions, if you want to find your omega limit set and hence all those equilibrium points, okay, to which the equation, the solution of your nonlinear evolution equation converges in long run, just solve your, what do you call, stationary problem. Once you have this, then you have your omega limit sets and you have all those points to which potentially the solution of the long-term behavior can converge actually. The solution of your nonlinear evolution equation can converge in long run. Okay, so this is it. And these calculations are true, but when your system is a gradient system. Okay, if your flow is not gradient flow, that is not going to be a topic to study in long run actually. Okay, we're gonna study them in a bit different manner later on. So I hope you got some sense of it. Okay, I know it's a bit tricky stuff, but it's interesting actually. And what you have to do, you have to apply these abstract results to the assigned evolution equations that you have actually, and see that whether the flows that you are studying are gradient flows or not actually. So thank you very much. So I will continue this discussion on convergence to the stationary solution in the next result, in the next what do you call lecture, and I'll prove the key theorem that I proposed actually in the beginning of the what do you call theorem, that that the solutions of the reaction-diffusion equation or nonlinear heat equation converge to some stationary solution to some equilibrium point, okay, which are the solutions of a stationary equation in H norm as t goes to infinity. Okay, so we'll prove that result in our next class actually. So I hope this is a bit enough for you. Thank you.